and it'll feel more intimate and all this. It's my very great pleasure to introduce two visitors who have been many times to the AMSAT Colloquium from Denmark. Steve, Peter and Steve.
Alex.
Alex, sorry, Alex. And I know them very well. And have a very bad memory. Anyway, thanks very much for taking the trouble to come across to see us. And you're going to talk to us about the Nexø II rocket, I guess. Looking at the thing. Yeah. Over to you. Thank you.
Yeah, I'll start. Thanks, and hello everyone. Thanks for joining us. So my name is Alex, and he's Peter Scott. And we will talk about the Copenhagen Suborbital Nexø II rocket, focusing on radios and electronics, because I think that's what's most interesting for you. How many of you have heard about Copenhagen Suborbitals before? Okay, so there's quite a few. But for those who have not, we are a crowd-funded space project with the mission to launch a person into space on a suborbital flight using our homemade rocket and space capsule. So it's an amateur space program, if you will. It started in 2008 with two guys working in a garage, and has evolved since then to, we are, I think, 60 people, plus minus, working in our spare time, building rockets and a lot of infrastructure that is necessary to make this happen. This graphics shows a timeline of our missions so far. Actually, all of these vehicles have flown to some extent, except the HEAT-2X in 2014, which burned up in flames in a spectacular failed engine test. I believe there is a video of it on the internet. It was very popular. But yeah, we learned a lesson, and that was actually a milestone, because the early years until that point were a lot of experiments, experimenting with various engine technologies like hybrids and solids. And beginning with the Nexø I rocket in 2016, the work has become more focused on bipropellant liquid engines using ethanol as fuel and liquid oxygen as oxidizer. Those two propellants are easy to acquire, or relatively easy to acquire and to work with, because they are not toxic like many other propellants. Both Nexø I and Nexø II were test flights for testing the engines, the manufacturing process, and the electronics as well for us. And we believe that that technology is quite scalable now to the big Spica class rocket, which one day will bring that person into space and safely down again, of course. Denmark is a small country, so we are not allowed to launch these big rockets from our backyard. And therefore, when we launch, we sail out to the Baltic Sea, to an area called ESD-139. This is a military shooting range where it's easier to maintain the range safety when we launch the rockets. We have done this for 6 years now, I believe, or since the beginning. And of course, this introduces new challenges, because we need a floating launch platform, a launch pad. So we have built one of those as well to make it happen. This is Sputnik, our maritime launch platform. It has its own engines. It can sail on its own, not very fast, but I think few knots or something like that. 3 or 4 knots, yeah. It can also be towed by another vessel, but it has been serving us well for many years. In addition to the launch platform, we also need a set of, or a fleet of support vessels to carry out the operation at sea. This is, I believe this is the complete fleet from the Nexø II launch earlier this year. The big boat in the middle is our new mission control ship, which is in charge of controlling the operations at sea. So mission control and coordinating with the boats and the air traffic in Malmö. The small vessels are smaller speedboats. They are used for transferring crew to and from the launch pad to maintain range safety, recover the rocket after splashdown, and also to take photos and videos during the operations. This is another picture showing the mission this year. And as you can see, this is an aerial photo, not taken by a drone, but actually a small aircraft. So we also use those during operations, mostly for photography and to have an overview of the launch area. A suborbital flight, so we are not going into orbit. It's just go up and come down again safely. This is a typical mission as it happens when everything goes according to plan. A rocket booster lifts the rocket until it runs out of fuel, and we have main engine cut off. After that, the vehicle will follow a ballistic trajectory. And shortly after apogee, the parachutes are deployed in a predetermined sequence. For Nexø II, we have tested both a balloon, which is a combination of a balloon and a parachute, suitable for those high altitudes. And later on, at lower altitudes, the main parachute is deployed in 2 stages. And for the first time ever, we have actually carried out a mission where we have pictures from all of these phases. So everything almost worked according to plan. And it started with a very nice liftoff, the rocket going straight up vertically. We got some nice pictures from high altitude. In this case, it was about 6 kilometers. This is the island of Bornholm, photographed from about 6 kilometer altitude and 35 kilometers away by the onboard cameras. Then after apogee, the parachute is deployed, and we have a nice and easy landing on the water. And finally, the rocket is recovered. So that's basically how each mission should go. And up until now, it was only low-altitude flights, but later, when we get to 100 kilometers, it will take a longer time. But still the same concept. And this was a basic introduction to what we do, and now Scott will talk about radio and electronics.
Yeah, so this is a outside overview of the Nexø II rocket. So it's pretty much the usual configuration. We have an engine, we have some tanks, and we have an electronics section and a parachute in the top. If we look inside it, this is sort of a shopping list. This is roughly the amount of components you need to build such a rocket. Slightly condensed a little bit. There's some technical details left out, but never mind that. But you need some valves, you need some tanks, you need some sensors of various kinds, you need a rocket engine, pretty important item, various pipe works, parachute, balloon. We need 3 airbag gas generators. We use them for deploying the parachute, actually. One of them for pushing the parachute out of the bucket, and 2 of them for popping the nose cone. That was the easiest way we could actually do it and get hold of pyrotechnics without a lot of legal issues, because these are standard components and you can buy them everywhere. And nobody complains that you have one, because everyone has one in their car. So it's a normal component. If we have a tiny piece of pyrotechnics, we need paperwork. Yeah, then we have on the electronic side some GPS receivers, video cameras, a number of antennas, an engine controller, which is one of the computers that I've made. We have jet vanes for controlling the flight. So the way we actually maneuver this rocket is having 4 jet vanes going into the rocket exhaust. So the rocket engine can't move inside the rocket frame. It's fixed. But the jet vanes will do the job. Then, yeah, guidance computer, batteries, wiring hardwares. And inside it, there's a lot of isolation material. So we basically padded the rocket after assembly with styrofoam. One is to isolate it a little bit, but the other thing is to make it float when we hit the water, because we want to recover it. And it has to be positive buoyancy. So the engine section contains of a engine controller, which is it's basically a Arduino Duo that we have redesigned to make it more mechanical solid. The Arduino Duo is not very good in a vibrating environment. So we made our own version of it, ruggedized it a little bit. This engine controller connects to all the sensors that are associated with the engine. So that's temperature monitoring, pressure monitors, and all the valves. And it controls pretty much the whole flight. From T-minus 30 seconds, that's where we start the engine controller and say, now you're in control, do whatever you need to do. And given a normal flight, we actually don't do anything else. It does everything required. So we just sit down and relax and watch the numbers on the computers and see something happens. And it actually worked. A picture of the CS-Duino, as we've named it. Yeah, lots of I/O pins. This is a small picture of the engine controller sits in this little box. This picture is quite cold because this is done during a cold flow test where we have the rocket on a test launch rail, and then we fill the liquid oxygen tank with liquid nitrogen instead. That makes it about 15 degrees colder, and then we let it stay there for about half an hour. The key goal is that we want to see if we can operate all the valves afterwards. And during that process, the whole bottom section of the rocket is actually covered in ice. But the valves are working. We clean them very thoroughly before we mount them. Just half a drop of water in one of those valves and they're stuck. We've seen that. Yeah, guidance system, it's pretty much the same as the engine controller. It's based on the same hardware. The only difference is that it controls different hardware. So it controls the jet vane servos, which are RC servos, although some of the strongest ones we can get hold of, but they are RC servos. Then we have the separation pyrotechnics. We have a tiny wire cutter, which initially holds the balloon in place, so it's connected to the rocket. But when we want to deploy the main chute, we actually cut the wire that holds the balloon to the rocket, and then it'll disappear and pull the main parachute out of the bucket. The pyrotechnics we have to push the parachute out of the pocket is just a sort of, if the balloon doesn't work, probably we can push it out forcibly. This guidance computer is working off a IMU that we luckily get sponsored from Analog, because we can't use one of the small ones you use for a gyrocopter or stuff like that. There's simply there's too much noise of them. There's too much drift. So we managed to get Analog to sponsor a $1,000 IMU for us, which will work for a short duration flight. So our guidance guy, he says, it'll work up to about a minute, perhaps a minute and a half. But after that, it's too much drift. Yeah, the telemetry stuff is completely homegrown, and I got one of the radios here. It's actually one of the flown ones, so they have saltwater damage from the landing. It probably still works, but I haven't tested it. It's based on a STM32 CPU. I'm using a standard 2.4 gigahertz transceiver from Analog, ADF7242. Even though it's a 2.4 gigahertz transceiver, it actually works pretty well on 2.3. So we're transmitting in the bottom end of 2.3 gigahertz for now. The signal from that is amplified, and then we send it out through a monopole antenna. The rocket itself has two identical radios, so and they transmit the same set of data. So there's redundancy on the radio side. The uplink part of it is using a Semtech SX1278 module, using a LoRa format, and we're running at roughly 10 kilobits uplink. The downlink is 250 kilobits, whereas half of that is actually error correction. So that gives us a very stable signal. Yeah, there's a tiny picture of the two radios and photo of them here. I got them up here if you want to take a look later. On the ground station, and by the way, the ground station sits on one of the ships, so it's a little bit more tricky to control the antennas than what we're used to, because one, the rocket moves quite fast when you're only 1.5 kilometers away from it, and secondly, the ship is actually rolling a little bit. But it works. We got a couple of Yagi antennas connected into a pair of USRPs, and using some GNU code that Alex wrote for the first part of the demodulation, and the packet framer is something that I've made afterwards. For the uplink, we're using the same Semtex module and a 20-watt power module from Mitsubishi. And that's, at least according to calculation, that'll work up to 100 kilometers and a little bit further. So we should be good to go. Yeah, here you see Peter Mortensen, who is operating the antenna tower. It was a reasonably calm day at sea, so it wasn't too bad. Yeah, a little bit on the telemetry system performance. You can see the two charts for the two receivers, and the two main contributors of data for the telemetry downlink is the engine controller and the guidance computer. They are by far the most talkative. We want to know what's going on in the engine, so we have telemetry transmitted in 100 Hertz intervals from the engine controller, and the guidance computer is running at, I think, 204 Hertz, which has something to do with the IMU, its native rate. During the entire flight, we had pretty much constant amount of data coming through, so no packet loss that we could really register, except we had one big gap in the middle where both computers decided to crash, or at least part of software crash. I'm not quite sure why, but I had to restart the software. And one of them didn't survive the restart for some strange reason. But yeah, that's why you have redundancy. But I still cannot explain why both computers, it's two physically separate computers handling each telemetry link, why both of them crashed pretty much exactly at the same time. They shouldn't just do that. But yeah, things happen. Okay, a little bit about our live streaming, because live streaming is a quite important part of our project, getting it out. So we have a number of video sources that we work on. We got some Evo cameras from US. We have some bone cams that are basically a webcam connected to a beagle bone. We have the cameras in the rocket, and we have a couple of handheld cameras with HDMI frame grabbers. And all of that feeds data onto the network, going into the first stage mixer we got. We have two mixer stages, and the second stage mixer adds cameras from the studio. It adds pre-recorded clips, telemetry data, graphics, and all that. That's added on the second level. The thing is, the first stage mixer is actually sitting on the ship, whereas the second stage mixer is sitting in the workshop in Copenhagen. And the guy controlling it is sitting in Copenhagen. So he's remote mixing or remote controlling the mixer on the ship, which is a little bit tricky, but it works. To do that, we have actually had to make a very long distance Wi-Fi network, because as Alex said, we are about 33, 34 kilometers out at sea, so we don't have any internet unless we bring it with us. So the two ships have a 5 gigahertz Wi-Fi link between them. That's sort of easy. We're only a couple of kilometers apart. But from the mission control ship and going back to Bornholm, that's where we got about 35 kilometers. And that's a challenge. We're using a 5 gigahertz Wi-Fi running on 60 centimeter dish in one end and a special antenna in the other end. And that's kind of, it works. We could probably go further if it wasn't for the reason that, or the minor detail that the Earth is round. We are very close to touching the water with the radio waves. I think at this mission, I think the minimum height we had from water surface to the line of sight was 6 or 7 meters. At those frequencies and those distances, to get out of the Fresnel zone, it was supposed to have been at least 25 meters. But it worked. We have packet drops a little bit, and unfortunately the live streaming system doesn't cope too well with it today, but that's something we'll improve on. Yeah, the receiver end, or the antenna sitting on the launch ship, or sorry, the mission control ship, is actually a modified, it's a standard antenna bought from Ubiquity, designed as a sector antenna. So usually it's upside down. I've flipped it 90 degrees and mounted on a prototype radar mount that I found somewhere, and made some control software for it so that we can point this one towards the ground station on Bornholm. And by having it oriented like that, it doesn't really matter if the ship rotates or moves a little bit around. It doesn't affect the signal, as long as I can maintain the right angle in one plane. We are planning on upgrading that to a proper patch antenna and adding free axis stabilization for it. But yeah, that's for the next launch in 2 years. Okay, over to Alex again.
Okay, so as Scott mentioned, live streaming is a quite important part of our mission because we are crowdfunded, and people who pay us money and the materials, they would like something in return. So we give them entertainment in return. And to that end, we have developed a quite extensive live streaming setup where we have a full production crew on the ships on sea and also back in the studio in Copenhagen. This includes speakers who interact with the live audience and explain what's going on and answer questions. But of course, in order to have good live streaming coverage, we also need a lot of cameras. So we have cameras all over the launch platform and the mission control ship. And they are, I think you called it first stage mixing, happens on board using our own mixer software that is available for download. And there's something new for the Nexø II mission. We also had 3 cameras on the rocket sending live video from the flight. They are feed number 10, 11, and 12, which is offline at the time of the screenshot there. Camera 1 was mounted at the lower section of the rocket at the end of this external cable canal there, looking down, providing a rear view. On this picture, you can see the launch pad as the rocket leaves the launch pad. Camera 2 was in the upper section, looking out through a small hole on the side of the rocket, providing a horizon view. This is basically what an astronaut would have seen through a window if there was one, or there will be. And finally, camera 3 was inside the rocket for filming the ejection of the nose cone and the parachute deployment during the flight. So how did we send the video down to ground, we implemented a system called DVB-S2. I'm sure many of you are already familiar with it from DATV experiments that you do. It's basically the system that is used in satellite television. That's an advantage because there's a lot of commercial equipment we can use and take advantage of. We had the 3 cameras sending their stream to a multiplexer, which created a single transport stream, which is then modulated to a DVB-S2 signal and sent through a power amplifier. On the receiver side, we used a commercial DVB-S2 receiver and some simple software that takes the stream from the receiver and distributes it out to whoever wants it. To take a closer look at the transmitter itself, so we have the 3 cameras. They were actually Raspberry Pi Zeros with the Raspberry Pi camera module, running AVC2TS software you may be familiar with. It's using the video compressor inside the Raspberry Pi, so it's all hardware-based, and therefore we can use it. We don't need a lot of computing power. The Raspberry Pi Zeros were connected to central computer or main computer through their USB connection, but running a USB network protocol. So they were actually IP cameras, not the USB cameras, but IP cameras. And the main computer was, that's an upboard with an Intel processor, because it also runs a software-defined radio modulator implemented in GNU Radio. So that it's a little more computing power. And also because we don't have time to optimize everything, so yeah, we just buy something that's faster. And so the GNU Radio modulator created a digital baseband, which we then transformed into RF using a HEC RF device. People often ask me why we use the HEC RF. Well, it's because we designed this, I think, more than 3 years ago, and back then there weren't so many options. In particular, when you know that the hardware you send up may not survive. So it's on a limited budget, you want to choose what's sufficient, and the HEC RF was perfectly fine for this purpose. And finally, our power amplifier was a Minikits kit you may be familiar with for 1.3 gigahertz. It was modified because we needed a little more, we needed to boost the power on the input side to have sufficient output. The receiver itself was a TBS 6902 tuner you may be familiar with. It's a PCI tuner card to a PC. And since we are using 1.3 gigahertz, we can use it without a down converter. It can tune from, I think, 900 megahertz to 2 gigahertz at least. We had an LNA in front of it to have lower noise figure. And the reason for choosing that particular tuner was that it has the widest dynamic range. If you look at the specification, its input range is quite wide. I think it's almost 60 or 70 dB it can handle. And that's good because the rocket initially is very close. It's about 1 or 2 kilometers away, but it moves, it goes up to eventually 100 kilometers away. So, software-wise, it was just a simple program called DVBlast, which does nothing else than takes the transport stream from the tuner and distributes it to the network to subscribers. So it's very simple and very efficient. This is a picture of 2 of the cameras we had. As you can recognize the Raspberry Pi Zeros and the cameras. The camera on the far end, it's my left, your right side, is using the Raspberry Pi camera module. The other one uses another camera module because we wanted a wide angle lens. So I think it had 90 degrees, if not more, angle. But it's compatible with the Raspberry Pi camera module. And this is the video transmitter as in this flight configuration. So it's the flight unit. The first board is the computer board. It looks like a Raspberry Pi, but it is the upboard with the Intel processor below the heatsink. So you see the HEC RF, and finally the power amplifier in a very nice custom-made enclosure. people ask, are you sure about those USB connectors? And but as it turns out, they are really very hard to pull out, actually. So we weren't worried about them. And the micro USB connectors we just soldered instead, so it wasn't a problem either. One of the things we usually have, or used to have with the rocket, was all the antennas sticking out from the rocket. So those black cones you see, there's enclosures for the monopole antennas. And people who handle the rocket, they usually quite hate them because they are always in the way. And as it turns out, they are not very efficient either. So for the video transmitter, we tried to design a patch array antenna that you can see on the lower section. It's it's the same similar concept as you have on Wi-Fi antennas, just 4 patches faced together to form a single antenna. And we had some professional guy measure or simulated and calculate the dimensions and how it should be to make it optimal. And this is how it ended up looking in the real life. This is what you could see below the blue shrink wrap on the picture in the beginning to protect it. And so to show the reason why we wanted this kind of antenna, here's a simulated radiation pattern of first an array of monopoles. As you can see, it radiates mostly up and down along the rocket, not so much to the sides. That's fine as long as the rocket goes straight up and the receiver is below the rocket. It's not a problem, but if the rocket suddenly becomes horizontal for some reason, then you lose the signal. Or maybe if the ground station is far away, it will have a weak signal as well. The patch array has a much better radiation pattern with very few nulls, as you can see. So yeah, we tested, we had new cameras, new video transmitter, and new antenna. You would not even expect that it would work, but as it turned out, it worked very well, everything. This is a screenshot from a video that you can go and see on YouTube. It shows the 3 camera feeds stitched together, synchronized for the whole duration of the whole flight. And we had basically very good reception for the whole flight with occasional dropouts due to spinning and also mispointing of the receiver antenna from time to time. I strongly recommend you go and watch the video if you haven't seen it already. And if we look at the data we logged during the flight, we have this graph where the bit error rate and the received packet rate. The blue curve on the graphs is the altitude of the rocket during the same time to correlate the events with what's happening. The bit error rate is something that we get from the tuner. And since we are using it in Linux with a Linux driver, it comes with an arbitrary unit. So we have no idea what the bit error rate of 400 means. What we know is, or what we can assume is that 0 means no errors and not 0 means some errors. And probably that 600 means more errors than 400. But what exactly, we don't know. But so therefore, the more useful measure is the received packet rate, where you can see a quite stable downlink of 8,000 packets per second. And if we try to explain why we have the drops, then the first one on the top is the small one. That's probably when the rocket is turning around and starts to fall. We have a small dropout. And then the large peak, I would think, is the deployment of the first parachute. That's basically an explosion is happening right next to the video transmitter, so a lot of shaking and moving going around. And the next ones, this is where the main parachute is deployed, so that's why the velocity suddenly drops and falls. And after that, the rocket is spinning occasionally, so that's why we have occasional drops. But we can safely say that this system worked very well, and we had also quickly reacquire what we observe on the videos is that you get the usual pixelation, or some parts of the picture is missing, but then half a second later is back to normal again, or a second later is back to normal again. So, and usually the higher symbol rate you use, the faster it reacquires the lock. So we haven't done detailed calculations yet, but I think this system with small modifications in the implementation can probably go up to 50 or 60 megabits per second. So it's will be scalable to many cameras or higher quality and higher rate. And yeah, that's what we had for today. And if you have any questions, we can answer them. Yeah.
I'm going to go with the first question, if you don't mind. Is your organisation a company, a group of enthusiasts, or?
It's a non-profit organization, so it's kind of like it's a club.
So it's a club? Yeah. Fantastic. I think you're all mad.
Yeah.
Obviously having great fun.
It's we have a quite large budget. I don't know if you know the number. I have an idea, but I don't know how accurate it is. But it's around maybe 150,000 euros per year. Yeah. But all that goes to material and rent and operations. Yes.
Yeah, fantastic.
And then of companies donating the materials.
Sure.
So, but no employees or paid employees at least.
Go, sir.
I'm interested to see your lower uplink and downlink. With a 20-watt PA on the ground and Yangian's airport, the link budget on that must be quite enormous. So surely I would have thought. So what sort of spreading factor have you been using?
Oh, I can't remember the number. It's 10 kilobits in, and the signal is half a megahertz wide.
Okay, so it's quite fast. Yeah.
Yes.
Any other questions? Neil.
Firstly, well done. That's ridiculous.
Thank you.
And especially on that budget. I was going to ask the budget question. That's having not built a rocket myself, but building a prototype hardware and stuff. That's an impressive achievement on a small budget. And since I can't ask that question because Jim already did, crowdfunded to that much money, where did you find this crowd?
Yeah, so in the beginning it happened by itself actually. So there was I think it was the first flight, the Heat 1X, which was broadcast by national television. It was basically when it was still 2 guys plus a handful of helpers, but it was broadcast on national television, and then the project became known. After that, there were problems with no more funds and no money, and people just started a support group, which is called the Copenhagen Suborbital Supporters. And there are, I don't know the exact number, how many people it goes up and down, but they are regularly paying. It's how, what's it called, that site? Patreon, yes, works today. It's basically the same. Yeah. But then there are people who donate once or twice or large amounts. So it's, yeah. But for sure, if we wouldn't have all the live streams, all the videos that are being produced, all the pictures, yeah, that helps. Yeah.
Next question.
I'm interested to understand how insulated your group is, or are you actually a collaborating group with other groups in other countries and other parts of the world? In terms of your ambitions, your long-term ambitions, you've been clear about what they are, and to what extent you're kind of sharing ideas and technological developments, or do you see yourselves as really quite a kind of boxed-in sort of organization?
Yeah, we are to some extent boxed in, but we do we don't have any direct collaboration with other groups, except for one group which is also based in Denmark. But we do talk to other teams. We have had a lot of discussions with the DARE team. And when they do parachute testing, we have actually been able to piggyback on that and do some of our parachute testing at the same day in the same lab. So we are in contact with some of the groups, but there's no kind of formal arrangements set up for it. We're also supporting a rocket group at the Danish Technical University, but it's on a consulting basis. They have our phone numbers, and we can arrange meetings whenever they have something they want to discuss, and we participate in their engine tests as observers, and give them ideas and hints and stuff like that. But it's nothing formal.
Okay, next question.
So, when could you launch a fun cube for us?
Oh, that's a very interesting question.
How high do you want it, and does it have to survive?
High as you can get.
1 kilo payload.
Yeah, we haven't made any plans beyond getting a person up beyond the 100-kilometer line and down again safely.
So that's about 80 fun cubes, yeah?
Yes, but that would be a rather short duration flight because it's done in about 15 minutes, including the parachute trip down. So it's not. Yeah, it's not really. There's not enough time to do testing. People have been sort of joking that we could add a second and a third stage to the rocket instead of a capsule and probably reach orbit. But we haven't done the numbers, and it's not part of the plan. Whenever we get past the major milestone of getting a person beyond 100 kilometers and down, then we might look at something.
Have you found a volunteer to be that person yet?
Oh, several.
Several.
And we get people applying regularly on the mailing list that want to be our astronauts.
But we are running out of crash test dummies, and they are very expensive. So,
but actually, the participant or our astronaut would get a bit more than Neil's 22 seconds of near weightlessness. We're talking about roughly 200 seconds of free fall. So, but you're enclosed in a very small compartment when doing it.
So I just want to ask, what is the diameter of your rocket? Because as you say, you're going to be enclosed in a very small compartment, and then also time frame.
Yeah, the diameter of the next rocket that we're building, right now we are designing it, but the intended diameter is 95 centimeters, which just happens to be a 3 meter length of metal rolled up in a roll. It's a nice round figure, and that is doable. You can fit an astronaut inside that space. It's tight, but it's doable. The time frame, we have sort of decided that we won't put a time frame on it. We built, and when we have launched the rocket with a capsule successfully a reasonable number of times without any incidents, or at least incidents we can't explain, then we might go to the point where we put a actually man inside. It will take time. We hope the first test launch of the Speaker class rockets will be in 2 years.
So is that the one you're designing now?
Yes.
There's not an intermediate?
No. We've talked about doing an intermediate step, but decided that it's basically a waste of money and a waste of time. It would just delay us. We wouldn't learn that much more.
Put a window and not rolled up sheet of metal, otherwise what's the point?
Oh yes, there will be a window, and we also have to put a door in it so we can get a person in and out.
Just take one more question and then we'll let the guys off the hook.
So it appears that you're sending the same rocket up multiple times based on what you were saying just now. Is there any limit on how many times you can send the same rocket up? I mean, what is the limiting factor there?
Well, yeah. Being a bipropellant self-cooled engine, the engine can kind of survive any number of launches we want to do. There's virtually no wear and tear on the engine. So it'll survive. The biggest problem is that we land on water, so we have corrosion from salt water, which will require, so we have to clean up the rocket very thoroughly after landing to be able to reuse it. But we hope we can reuse it at least a number of times to keep the materials cost down. But we'll probably end up building a couple of them during the process. Because when we get to launching a person, we'll probably want to do that on an engine that hasn't done too many runs.
Okay. I'm going to call a halt there, if you don't mind, because time moves on, and we've got the wonderful AGM coming up. Thank you very much, you two.
Thank you.
Not only are you rocket science, you're mad rocket scientists, if you ask me. Thank you very much. Very good. Okay, that concludes the presentations for this afternoon. We will start in here the annual general meeting in just a